Hi everybody and welcome to today's class on managing biodiversity under uncertainty. This is an area that I'm particularly interested in because it's one of the main components of my own personal research. A lot of what I do, especially in the field of conservation planning, is working out, well, how do we start to deal with what we call imperfect information? So when we don't know exactly what's going on, how do we actually start to do any sort of management or initiate any sort of policy? So that's a little bit about what today's class is about. Okay, so without any further ado, I will just start the sharing screen. Where's it gone? Here we go. Okay, so by the end of the class, you guys should be able to describe the scientific method and apply it to a real-life example, compare inductive and deductive reasoning and illustrate how it relates to the scientific method, evaluate the uncertainty in conclusions based on scientific data, and describe the consequences of some different attitudes towards uncertainty. Okay? It's doing that again, isn't it? So, before we go any further, I'm just going to put my laser pointer on. There we are. Okay, so in an ideal world, any management decisions that we make would be based on perfect knowledge and outcomes would be absolutely certain. So we can think about this not just in biodiversity, but in any sort of prediction we want to make. So for example, the weather is one of the biggest things in that. Some of the biggest supercomputers on the planet do nothing but try and predict the weather because it's got so many variables, so many things happening that trying to predict the weather is actually quite tricky. So at the minute you get, say for example, you get information on temperature, wind patterns, ocean currents. You put those all together into a forecast model and you can predict hurricanes and things like that. But there is this sort of nice little foible about the fact that, well, we know about chaos theory and the uncertainty that is associated with tiny little events. And there's this idea that, okay, well, a butterfly could flap its wings on one side of the Atlantic and that will change the air currents in a tiny, tiny way, but it's enough to cause a hurricane on the far side of the Atlantic. So there's these little tiny bits of chaos that we don't understand inside our models, and so it makes prediction is uncertain. Whenever we make any sort of predictions, we cannot be 100% certain that what we're predicting is actually going to happen. And there are multiple ways we might think about assessing uncertainty. So to assess uncertainty, the first thing we need to think about is we need to understand how knowledge and data were obtained. So a lot of data is collected by a person just going out into the field and making observations. That person is just having a look at what's going on around them and making notes about what's happening, and as a result we can treat that as a form of data. But in this sort of system, there's so many sources of uncertainty. So for example, who is the person making the observations? Are they a trained expert? Are they just some random off the street? How good was their eyesight? Were they feeling okay that day? Were they desperate to just get the data done and go home because they weren't feeling 100% and they just wanted to get out of there? Was it always the same person? All of these aspects bring in different parts of uncertainty. We might think about, so if just having a person take measurements, there's little bits of uncertainty, you can add human error into that. What if we just use an automatic recording station like this? This is a weather station. So a lot of the data on weather that we have is not collected by people. People aren't going out and measuring the rain and measuring the wind speed by hand. We have these continual monitoring stations. There's actually one on Utah State University campus. You can go and have a look at it. It's just past the student centre. But this thing, it's got this little doohickey here that's collecting wind speed, and this is measuring rainfall, it's measuring temperature. So this machine, you say, well, it's likely to be more reliable than the person. But then we have to ask, was the machine calibrated properly? Was it set up properly? When was it set up? Has it started to degrade? Are its sensors falling apart? Does it need maintenance? All of these things are potentially aspects of uncertainty. We then might think, okay, so rather than measuring things in the field, we can conduct an experiment in the field. So this is one of the famous grassland experiments take place all over the world. And what you do is you plant little thickets of different types of plants, and you measure what happens, and you can control the number of species that are going into each plantation. You can control the nutrients that are going in, how much access to sunlight it has. So then you're controlling the environment an awful lot more rather than just taking random observations. But you then have to ask yourself, well, is this really a natural system? Is it, because we're controlling it so much, is it still subject to the same processes that a natural system is? Also, when these plants were planted, was it the same person each time? Were the people equally trained? These are all potential sources of uncertainty. And we need to think about where they're coming from. And when we're looking at the results of data and we're trying to interpret them, we can have two types of reasoning. We can have what's called inductive reasoning. And inductive reasoning, you're collecting observations or data about the world around you, and using these observations, you make logical generalizations. So, for example, you might go out and looking at your binoculars, you notice that a particular type of goose comes to a particular lake at the same time every day. So you can start to suggest, okay, using inductive reasoning, this goose comes to this lake every day. This goose likes water, and it likes water at this particular time of day. Or you might be able to go, okay, we've collected data on rainfall and wind speed for months and months and months. I now have a decent idea about what the wind speed and the rainfall are in this particular location during these months. So what we're doing is we're collecting data and we're making logical generalizations. Second type of reasoning is deductive reasoning. So what we do with deductive reasoning is we use existing facts, or we make hypotheses, and we use those to make predictions. So we might observe, let's see in our rainfall data, we observe, okay, there's more rain or precipitation coming down in March than there is in August. We know this, we've collected those data, so what can we do for our deductive reasoning? We can make a prediction to say there is more precipitation in the spring than there is in the summer. This is using existing facts to make a prediction about the future. So the big difference between these two is inductive reasoning is looking at data, looking at observations, and using that to explain what's happened or what's happening now. Deductive reasoning is we're using these initial data to make hypotheses about the future, but we might not know what the mechanism or what's causing them. Okay? Right, let's have a go at a couple of these. So a bit of inductive reasoning. We're not going to use our clickers, just think about it in your head. So using inductive reasoning, can you predict the next number in the pattern? So the pattern of numbers is 0, 3, 6, 9. So what do you think is going to be the next number? Just give you 5 seconds on this. Okay, well I suspect the vast majority of you said 12. And yeah, I mean, if it's going to be anything, it looks like it's going up by 3 each time. But can we be absolutely certain it's 12? Or could it actually be 0 and this pattern is just repeating? So it goes 0, 3, 6, 9, 0, 3, 6, 9. We don't know. What we're trying to do is work out, given what's happened so far, what's going to happen next. Is it always going to go up by 3, or is our pattern a repeat of these 4 numbers? We might suspect, and most of the evidence would imply, that it's going to be 12 because we've observed on 3 occasions it going up by 3 each time. But that's more than likely, but we can't be absolutely sure. Okay, let's try another one. Could you draw the next figure in this pattern? So have a quick look at the pattern. What is the next figure going to be? Is it A, B, C, or D? I want you to really think about this. I'm going to give you 15 seconds on this one. Okay, so I'm sure some of you put B, I'm sure some of you put A, but the correct answer is actually D. We cannot be sure. And the question is, why can we not be sure? Unlike the last example when we had a pretty decent idea, in this one we really cannot be sure. And the reason we can't be sure is because of this number 1. Because if this number 1, this first square, is actually pointing upwards, it means we go upwards, on the side add 1, upwards add 1, on the side add 1, in which case we would expect it to be B, because then it would be upwards and add 1. But if this one is not pointing upwards but is actually on its side, and it's orientated not horizontally but vertically, then it would be 1 horizontal, add 1, stay horizontal, then add 1, go vertical, then add 1, go horizontal, and to follow the pattern we would add another 1 and stay horizontal, in which case we would have this arrangement of squares here. So we have no idea whether or not this first square is arranged vertically or horizontally. And depending on whether it's arranged vertically or horizontally determines whether we switch vertical to horizontal each time or whether we switch vertical to horizontal every 2 times. In other words, number 5 has equal chance of being either A or B, and we just can't figure it out from this pattern. We're too uncertain. So you have to sometimes think about, okay, where are these sources of uncertainty coming from? What do they mean? How confident am I in them? And how big of a problem actually are they? In the previous example, when we had the numbers, we say, oh, there's a slight chance it could be just a repeating pattern, or it's more likely that it's just adding 3 each time. This time, we have absolutely no idea, because we've no idea if this one is orientated vertically or horizontally. Okay? So we'll just add another fake clicker question. It's important that we get some of these ideas lined up front. So in science, what is a hypothesis? And I don't mean in regular day-to-day language, I mean actually in science. So what is a hypothesis? Is it A, a belief in how the universe works, i.e. dogs go to heaven? B, a testable idea based on previous evidence? C, a prediction about the potential for future discoveries? Or D, an explanation for the results of an experiment? I'll just give you 10 seconds on this. Okay, well the correct answer of what a hypothesis is in science is actually B. A hypothesis has to be a testable idea based on previous evidence. So the crucial thing in there is testable. In order for a hypothesis to actually be a hypothesis, it does have to be testable based on previous evidence. So say for example, we're currently in where I am now, we're in the springtime. I'm in the month of February. You might be watching this in the month of March. So let's think of a hypothesis based on rainfall again. So based on previous evidence, from what I've observed from living in Logan for 6 years, previously, I've observed that there's more rainfall in April than there is in August. So I'm going to hypothesize. So a hypothesis is a statement of a testable idea. So I hypothesize that in 2021 there will be more rain falling in April in Logan than there will be in August. This is an idea based on my experience from living here, and it's testable. I could set a little bottle out on my front porch and I can measure the amount of rain that lands in that bottle in April. I can measure the amount of rain that lands in August, and I can test my hypothesis that more rain is present in April than in August. So it's a testable idea based on previous evidence. The critical bit is it must be testable. If it's not testable, then you're descending into the realms of philosophy, because there's no point making a statement in science about something if you can't actually test it. It's not worthwhile. Okay, so that's a hypothesis. Now let's go for another one. So in science, what is a theory? So is a theory an accepted idea that ties together multiple pieces of evidence and facts? B, a belief about how the universe operates based on no evidence? C, a faith-based preconceived idea that is yet to be tested? D, an explanation of phenomena based on personal moral values? Or E, a state of mind where a person believes something to be true with or without evidence? Just give you another 10 seconds on this. Okay, so this one's a little bit vaguer because theory is also a word that's used in day-to-day English. But in terms of science, what we mean by a theory is an accepted idea that ties together multiple pieces of evidence and facts. So theories are really important and interesting parts of science because what they are is they've taken a whole bunch of bits of evidence and using those bits of evidence, they combine it together to make a theory. So some of the ones you might have heard of are the theory of evolution. This is based on evidence from the fossil record, evidence from molecular biology, evidence from the results of lab experiments. All these little bits of evidence all tie together and they generate and they provide evidence for the theory of evolution, the idea that species change through time based on natural selection. Another one might be things like the germ theory of disease. So we have this idea that a lot of diseases are caused by pathogens entering the body. Those pathogens do harm to the body and they cause disease. That's known as the germ theory, and that's based on, okay, we see people with these particular symptoms and with these particular consistent illnesses. When we test them, we find that they have these pathogens present in their body. So we have these two bits of evidence, the presence of a pathogen, the symptoms the person is expressing. Those are tied together in the germ theory of disease. Other ones are things like the theory of gravity. Why do objects fall? When I drop them, they fall onto the floor. Why do planets orbit stars in the way they do? Why does the moon orbit the Earth in the way it does? Well, it's because there is this force that moves bodies around, and large bodies attract smaller bodies of light, smaller bodies, and so as a result, we have the theory of gravity. So a theory in science is an accepted idea, ties together multiple pieces of evidence and facts. Okay. So now let's talk quickly about the scientific method. So the scientific method is the way in which new knowledge is acquired using science. And the basic process looks like this. First up, we go and use some observations. We make some observations about the world around us. And we use those observations to make hypotheses using inductive reasoning. We use the hypotheses. What we're doing is predicting the consequences of something to happen, often in an experimental setting. And this is deductive reasoning. We then collect data and we determine if our predictions are supported. So we go through a whole series of processes. So for example, let's think about the geese. We might say, I went out a whole bunch of times and I went to a lake and I saw geese arriving at this lake at a certain time of day. So I make a hypothesis. Geese like water. Geese will arrive at water. Geese will come to water. So I design an experiment. I make a fake lake out in the middle of nowhere. I put some water in it. I stick some reeds in it. I've made an experimental lake. And then I watch and see if geese arrive at the same time of day. I'm testing my hypothesis that geese require water. I collect data on the geese arriving, and then I can determine if my predictions about geese needing water are supported. And I can start to see, depending on if I see geese coming to the lake, if they do arrive, I can say, oh, it seems that geese do like water. If the geese don't come to my fake lake, well, there was something else about the original lake that the geese liked that I didn't pick up. Maybe geese only like lakes with a certain type of plant, and I didn't put that plant in my fake lake. What I'm doing is I'm collecting data, determining if my predictions are supported, and I can make changes as necessary. And this is very useful for generating knowledge, but we have to be careful because there are serious sources of uncertainty that could become very problematic. So, for example, our initial hypotheses could be wrong. Say, for example, this is how we end up with the flat Earth theory and the moon and the sun orbiting the Earth. So let's think about how we might end up there. Say I'm a person in, let's say, the 4th century BC, and I wake up every day and I look outside and this big yellow ball seems to appear in the east and traverse over the top of the sky during the day, and then it goes below the horizon at night, and then this other smaller ball appears and it appears at night, goes over the top, and it disappears by morning. So I start to collect data on multiple days. I get up multiple days and I observe every day this yellow ball of light goes over the top. So what do I start to suspect? Well, I hypothesize there is a small yellow ball in the sky that is going round the Earth. It appears in the morning and disappears in the evening. I wake up the next day after my prediction to test my hypothesis. Yes, that sun appears and it goes over the top. Because my initial hypothesis was wrong, I only saw that my hypothesis was there is a yellow ball moving round me, not I am standing on a gigantic ball and it is turning round, and that yellow ball is actually much, much further away, and I'm going round it. But both those two arrangements would generate the same observation. Okay, so our source of our initial hypothesis that we're testing could be totally wrong. In addition, we might have things, what we call a spurious correlation. So when we go and collect our data, we find a correlation that is there purely by chance. One of my favourites is this spurious correlation here. So, what type of graph have we got? Well, we've got a line graph and I suppose a scatter plot. What are the axes? Well, on the x-axis we have the number of pirates globally, and this is approximate. On the y-axis we have the global average temperature. And what we see through time, we're starting in 1820 and we're going up to the year 2000, we see in 1820 there were lots of pirates, about 35,000 of them, and the average global temperature was quite low. Then over time the number of pirates has gone down and global temperatures have gone up. So what does this mean? Well, it means that if we want to halt global warming, what we do is we get hold of more pirates. If we get more pirates, the temperature will go back down again. I mean, that's obviously not the case. I mean, it's what we call a spurious correlation. It just happens to be that through time, the number of pirates has gone down because we've got increased policing of the world's shipping. And also through time, average global temperature has gone up because we were burning fossil fuels. So these two, the X and the Y, are totally unrelated to each other, but we found a spurious correlation. Both these two things, pirates have gone down and temperatures have gone up, have occurred at the same time. So we start to say, oh, it's a spurious correlation. Also, we might have a situation where if we do have an experimental system, are the results from that experimental system actually representative of the natural world? So, for example, this is one of those grassland experiments. This is David Tillman's famous grassland experiments, where they plant all these different sorts of plants and they manipulate biodiversity on each one of these plots, and they can draw conclusions about the relationship between biodiversity and ecosystem functioning. But are the results from this experiment true in the natural world? This is a highly modified experiment. The natural world is not nearly so controlled. So as a result, we have these various sources of uncertainty. And all these levels of uncertainty start to pose really serious questions, especially when you're trying to conserve rare species. Because often the problem with rare species is that we don't have much information on them. First of all, they're rare, which means there's not many of them. So that means observations are hard to come by. We might not have many observations of the species. Also, because it's rare, it might be relatively unstudied. We don't know much about its life history and things like that. So this really starts to bring up problems about how do you conserve rare species. And we'll just talk here about a little bit of a tale. So, we're going to talk first up about something called the ivory-billed woodpecker. Don't know if anyone's ever heard of the ivory-billed woodpecker, but it's an absolutely beautiful woodpecker. It's one of the biggest, it is the biggest woodpecker that's ever existed in the US. It was all through the south of the US, and it's a very, very charismatic bird indeed. It's sort of this lovely black and white colour with this huge red sort of Mohican hairdo on the top. So it's a really cool bird. Because it was so charismatic and it's big, it was highly prized amongst bird watchers. Lots of people went out to go and find this thing. You can find notes about people that have seen these ivory-billed woodpeckers. People talk about, they draw the colour schemes of them, they talk about what they look like in flight. They've made these notes. People have observed these things. These things were flying around all over the Deep South. Lots and lots of different folks making observations of them. However, what is going on with the ivory-billed woodpecker now? So, this series of figures here, unfortunately, tells a little bit of the story of the ivory-billed woodpecker. So, first of all, this map. This map is the southeastern United States. This black line is the basic historic range of the ivory-billed woodpecker. So it's where it always used to live. All these dots are observations of the ivory-billed woodpecker, places where it was actually confirmed as being seen. If you want to see an ivory-billed woodpecker yourself, you can actually go and see one. There's one in the Natural History Museum of London, and there's one in the Natural History Museum in the Smithsonian. It is stuffed, and it's very dead, but it exists, okay? And it used to survive in these marshy swamplands all through the southern US. And each one of these dots you can see, it's also got the time at which the observation was made. If we plot when specimens were collected, these are museum specimens that were collected because they're so charismatic. We look at these collected specimens, we look at the year, you can see the ivory-billed woodpecker, there was lots of specimens collected in the late 19th century and then into the 1900s, but the last real specimen was actually collected about 1932. And that was found in Louisiana. So the last time there's an actual confirmed sighting or observation and collection of the ivory-billed woodpecker was 1932. So what's happened to this bird? Why haven't we seen any more? Why don't we observe it anymore? Why have no more specimens been collected? Well, there's two possible outcomes. One, the bird is incredibly rare. So it's so rare, no one is seeing it anywhere. And if it is that rare, then we should be doing everything we can to conserve it. We need to be applying lots of resources into restoring the habitat for this species so that its populations can come back up. There is one other possibility, and that is this bird is not rare, this bird is dead. This bird is completely extinct. And if it is totally extinct, then we really shouldn't be investing resources trying to restore its habitat and bring its populations back up again, because it's already dead. So if the bird is incredibly rare, we should be doing everything we can to conserve it. If the bird is dead, we shouldn't be doing anything to conserve it. So as a result, we have this unfortunate piece of uncertainty where the fact that you cannot prove that absolutely that something is definitely dead makes it very hard when you're talking about conserving rare species. Because although you can find the absence that something is alive, so you've got the absence of proof that it's alive, that doesn't constitute proof that it's dead, if that makes any sense. It might be you're just not looking hard enough, or you just don't know what it is. So the ivory-billed woodpecker has not been seen since 1932 and lives in this area. When we actually talk about the ivory-billed woodpecker, now the general consensus in the scientific community does agree the ivory-billed woodpecker is extinct. It no longer exists. It hasn't been seen since 1932. Loads of people have been looking for it around Louisiana. It is done. It is out the game. It is gone. So, there is no evidence the ivory-billed woodpecker is still alive. However, the last one of these things was seen in 1932, which is what? About 80, I can't do that math in my head, 97 years ago. So it was a long time since it's been seen. But there is a story of another species. While there's no evidence for the ivory-billed woodpecker still being alive, there is another story of a species called the night parrot. Now the night parrot is a ground nesting bird. It's a little bit big, about the size of a small dove. It lives in the ground, and the last observed sighting of a night parrot existed in 1912. So that is 109 years ago. So the last night parrot was seen in 1912. This was a bird that was totally considered extinct. It's an Australian bird. No one had seen it for 100 plus years. This thing is extinct. Everyone assumed it's totally done. But the night parrot was interesting because it had this very unique plumage. So although a lot of parrots are very brightly coloured, the night parrot was just the one colour, green, but it had these incredible feathers with this black and yellow banding on them, which is not seen pretty much in any other parrot species. The bird was totally assumed to be extinct, and then this feather turned up in 1999. So the bird hasn't been seen at this point for nearly 100 years. And then someone finds this feather. There are museum specimens of the night parrot, so they were able to take this feather and compare the feather to these specimens that are stuffed in museums, and they found, you can see this very characteristic green colour with the yellow and black bands. I mean, this is pretty iconic as a night parrot feather. So this feather had showed up in 1999, and suddenly the birding community went crazy. They were just like, what on earth? Like, where is this piece of evidence of this extinct bird come from? Now, there was a problem, and that this feather was found on the front of a semi, so a delivery truck. The driver had come off the delivery truck and found this feather embedded in the grille on the front of the truck, and was like, oh, that's quite interesting, so he sent it to a museum. When the museum asked where he'd been, that semi had just completed a 2,900-mile trip from Mackay up in Queensland to Perth in Western Australia. So that truck had just completed basically a transcontinental trip through two of the most remote places on Earth, going right the way through Queensland and into New South Wales, right the way through the middle of the outback. It then crosses over the Australian Bight and goes back through the hardcore outback in southwestern Australia. So this truck had just to give you an indication of how big this is Australia. This map is California, Nevada and Arizona. So there's California there. So this truck had basically just driven 3 times the length of California, and somewhere on the way it found this feather. So though it's evidence the bird exists, it wasn't massively useful to know in terms of where the bird was, because it had just picked up this feather at some point on this massive monster trip. But it did give some evidence the bird was alive. And so this feather was the start of a 15-year quest for a birder called John Young. Now, I actually met John Young in Sydney in 2015. He is just an incredible character. He is the most sort of quintessential outback Australian you'd ever seen. And he's also absolutely obsessed. He's one of these people, gets an idea in the head and just goes with it. So when John had heard the feather existed and it had been found, and when he was allowed to go and see it, it started this 15-year quest. He was determined that the night parrot that hadn't been seen at this point for about 100 years was still alive somewhere. And so John set off, taking his pickup truck and his little ATV, and he spent an estimated 17,000 hours searching in the most remote parts of the Queensland and Western Australian deserts for this elusive night parrot. Bearing in mind at this point, no one had seen it for about 100 years. Now in the early 2000s, John thought he had heard a night parrot. Although he didn't really know exactly what the call was, he suspected he'd heard a night parrot, and he said all he'd heard was he'd heard the call at night of something that said in words it's gut gut or gut gut gut. So remember, this bird is nocturnal, it's very elusive and it hides, and so he's literally searching for a needle in a haystack. Now in 2013, John claimed to have actually found a night parrot. And he took these pictures of a night parrot in the evening, and he showed the photos at the Queensland Museum in Brisbane. Now when John first showed the photos, they were questioned. And the reason for that was that in 2006, John had actually got into trouble for doctoring pictures of another rare bird. So John had been doctoring pictures of the fig parrot. This was John's initial picture of the fig parrot, which is a very rare species of, another rare species of parrot, but it looks quite similar to another species of parrot. And he looks like he doctored these images. And so the images that he'd taken were sent to Professor Gail Spring, who is a scientific expert, scientific photographic expert at RMIT, so the Royal Melbourne Institute of Technology, and Gail came back with the following. So running just some basic analysis on it, there were several highly suspicious areas. I found out later that each of these highly suspicious areas were the areas that actually defined the species of parrot. So John had previously claimed to have found a very rare parrot, but on subsequent analysis it looks like his photos have been doctored, so everyone was really suspicious about his 2013 pictures of the night parrot. To the extent where Sean Dooley, the editor of BirdLife magazine, came up with the following statement, saying, "If John Young's claims prove to be correct, this is the world bird-watching equivalent of finding Elvis flipping burgers in an outback roadhouse." So the fig parrot incident, combined with the fact that the night parrot had not been seen for 100 years, essentially meant that nobody believed John, even though he had pictures. So in 2013, John actually made the decision to release the first night parrot pictures to the public. And here's the first picture he took. So remember, this is the illustration from the museum specimens, and this is the bird that John had found. So this looks bang on like a night parrot. But given the fig parrot photo doctoring, many people actually refused to be convinced that John had found a night parrot. So in 2015, John teamed up with a university researcher called Steve Murphy, and together they went back to the location where John had taken the photo, and they caught, tagged and videoed a single night parrot. Now this link is in the slide, so I suggest you go and have a look at it, but I'm going to show you the video as well. So let's stop sharing that. Where's my cursor gone? Hello. Let's share another screen. Of course, I've got far too many things open. Where have I put it? There's photo booth, Microsoft. Okay, where have I put it? Okay. Let's just do the desktop, do the second desktop, and on this desktop we will go to the internet. And here it is. So you should, give me a second, let's make sure we're sharing screen. Oh. Okay, you guys should be looking at a bird. Let's have a look. Let's play this. You can hear that call, like grit, grit. And there it goes. So the man in that video was Steve Murphy, who is the scientific researcher. So we had his word for it as well, and we have the video of the actual night parrot. Off you go. So at that point, not only do you have the picture of the night parrot, we now also have a video, and we have the testimony of a scientific researcher. Let's go back to sharing the PowerPoint presentation. Okay, so at this point, the evidence is pretty conclusive. Even though at this point, that bird had not been seen for 103 years, now they've actually found it, tagged it, videoed it. Now then the question became, so this bird hadn't been seen for 100 years. It's incredibly rare. It's a little tiny night parrot found in a remote part of Queensland. Then the question is, how do you manage such an incredibly rare but famous species? Bearing in mind the night parrot, birders have been looking for this thing for 100 years. Well, this species, the night parrot, was found on a private ranch. And the private ranch was owned by this bloke. And this is Mr. Pullen. Now, Mr. Pullen was kind of an interesting fellow. Obviously he's an Indigenous Australian, and he lives in this ranch. And for some Indigenous Australians, the dingo is an incredibly iconic and important species. For many European Australians will kill dingoes on their farm or on their ranches because they're worried about them taking sheep. But for some Indigenous Australians, they're incredibly important. So Mr. Pullen had this situation where he hated feral cats with a fiery passion. So feral cats in Australia are not like your domestic puss cat that you have at home. They weigh about twice as much as a domestic cat, and they're these big, gigantic, brutal death machines. This guy, Mr. Pullen, hated feral cats and would do everything he could to eradicate them. But he also loved dingoes, so he actually encouraged dingoes on his ranch. And John Young believed that the owner's hatred of feral cats and the love of dingoes had kept this parrot alive. Because cats aren't native to Australia at all, and these cats will attack and eat ground-dwelling birds. So a night parrot is it's assumed that feral cats are what drove night parrots extinct in the first place, or perceived to be extinct. But the fact he'd encouraged dingoes, those dingoes were keeping the cats away, and the fact he was killing any cats he saw meant that this parrot probably survived there. But what they didn't want is all of the world's birders descending on Mr. Pullen's ranch, disturbing the fragile ecosystem and potentially driving the parrot extinct. So for 3 years, John refused to tell anyone the location of the ranch where he'd found the night parrot, and Mr. Pullen swore to secrecy. He said, he didn't even tell his friends that he had these night parrots on his ranch. Nowadays, the night parrot now has its own dedicated private reserve. It's named after the owner, so it's called the Pullen Reserve, and it's 56,000 hectares in central Queensland. You are not allowed to enter the Pullen Reserve without quite some serious permission. The fine for illegal entry is 350,000 Australian dollars. Australia does not mess about when it comes to its fines, and they will and have imposed this fine on people who have tried to enter. It's believed that the population on the Pullen Reserve is only about 30 to 100 birds. Interestingly, after they came up with the idea that it was the dingoes and the keeping cats off the land that had allowed the bird to survive, they actually went and sourced out other places in Australia where this same situation had happened. They have actually now found another population of night parrots. So, considering it was considered extinct for over 100 years, there's now at least a couple of populations. But we have to remember that proving the absence or extinction of something is very difficult. So we then have to ask ourselves, well, how should we protect a species if we don't know where it is, or even if it still exists? Do we want to be investing resources in protecting a species if that species is already extinct? Well, what we can do is we can start to use decision theory from economics. So economists have been wrestling with these sorts of problems for ages. So in terms of conserving a rare species, we do it on what's called a 2x2 factorial design. So we ask ourselves, should we conserve it? Yes or no? Does the species exist? Yes or no? And depending on which of these we pick, we see, okay, if we conserve and we choose yes and the species is still alive, then yes, it was a correct decision. If we conserve, we decide to, it does exist, but we don't conserve it, well, then the species is placed in danger. If we do conserve it, but the species doesn't exist, it means we're paying a conservation cost, but those costs are wasted because the species isn't present. If it doesn't exist and we don't conserve, that's true. We need to work out what the consequences are of each of these different options. And this is basically the exact same process that's used in the stock market. In the stock market, you're always asking yourself, is this stock going to go up? And should I buy some of it? Or is it going to go down, i.e. extinct, in which case I shouldn't buy some of it? So you're always making these same sorts of decisions. To the extent where I used to work for a group in Australia called the Centre of Excellence for Environmental Decisions, and their whole shtick was using principles and ideas that have been used in the stock market for decades and applying them to conservation ideas. And that's one of the projects that I actually did when I was out there. And the concept that I did was, how do we start to incorporate uncertainty in conservation? And I said, well, develop this idea where we can incorporate uncertainty through the concept of scenario planning. And what I was looking at, because it was a nice charismatic idea, was the relationship between armed conflict and biodiversity. And how does armed conflict, how is it related to biodiversity? How does it impact biodiversity? And how do we conduct biodiversity planning when we have the risk of armed conflict present? So, We start off with the general principle that armed conflict is bad for diversity. This is biodiversity in the background. This is it receiving an awful, a sort of family-sized portion of American freedom. That is not going to be good for the forest in the background. As a result, if you have armed conflict occurring, it often takes quite a serious toll on diversity. And we looked at some of the data and we found out that, well, unfortunately, 90% of armed conflicts that happened between 1950 and 2000 actually occurred in biodiversity hotspots. That's globally. There are many reasons why this might be. I mean, one, biodiversity is, if you are a small armed militia, highly biodiverse areas like tropical rainforests are great because you can hide an entire militia inside a rainforest and it's very hard to be found. Satellite imagery can't even penetrate the rainforest, so you can't see them from space. Thermal imaging doesn't work in the tropics. So as a result, biodiversity hotspots are good places because you can hide a militia. Also, you can support a militia in terms of food and things like that based on what you can harvest from highly biodiverse areas. And also, you can sell diversity to make money. Rhino horn. You can sell bits of diversity to use to fund your armed conflict. As a result, we've got this unfortunate situation where lots of armed conflict happens in biodiversity hotspots. I actually mapped this in Africa. So this is the continent of Africa on a global scale. Africa is huge, by the way. It's the biggest continent in the world. So here is a map of conflict risk for Africa. The red is very high, white is low. We can see this is the Democratic Republic of Congo, Uganda, Rwanda. Here's Somalia, here's the Niger Delta. This is the beginning of the Arab Spring, so it tells you when this data is from. So as well, we've got these areas of high conflict. We then look at where the diversity exists. Dark green is high biodiversity, light green is low biodiversity. If you overlay those two, you find, unfortunately, yep, the diversity exists where the conflict risk does. So we've got this situation where highly biodiverse areas spatially line up with areas of high conflict risk. So given this correlation, we can look at the consequence of three attitudes towards risk when we're talking about conservation. We can either do conservation where we ignore the risk of armed conflict, we just pretend the world is wonderful and happy and safe and nothing ever goes wrong. We can identify areas of high conflict risk and choose to just avoid them and say, well, we're not going to do any work there because it's just too risky. Or we can account for the risk and base some of our actual actions on the ground on our ability to predict and see where risk is going. And what we found was, if you either ignore risk or avoid risk, you can end up losing up to 50% of the mammalian biodiversity from Africa. If you ignore risk, you actually end up not doing enough effort, and so you end up with these things getting killed off. If you avoid risk, you end up moving away from all the biodiverse areas, and so as a result, you lose a lot of species. Conversely, if you account for risk, you actually get up to about 96-97% of the biodiversity. So by doing these different attitudes towards risk, you can look at how it affects conservation outcomes. So what we found is that, well, when dealing with uncertainty, it's better to account for it rather than avoid. I actually gave a TED talk on this piece of work. It's still up on YouTube now. If you either just go onto YouTube and look up Ed Hamill, TED, or you can click this link. It's in the slides that I've uploaded online. That will take you and you can watch my TED talk if you like. Okay, so by the end of this class, you guys should now be able to describe the scientific method and apply it to a real life example. Compare inductive and deductive reasoning and illustrate how it relates to the scientific method. Evaluate the uncertainty and conclusions based on scientific data. And 4, describe the consequences of different attitudes to uncertainty. Okay, that's where I was going to get up to today. I hope you enjoyed it, and I shall see you next time. Have a good one.